This is the shocking part of it, learning about the aerospace data facility in Colorado that, by the way, was classified. Its existence was classified until 2008. That's where the data comes in from the satellite that sees the hot rocket exhaust on the ICBM as it launches in less than a second. So in a fraction of a second from the time that there would be a rogue launch, in my book I use the North Korean scenario, right? Mm-hmm. A fraction of a second, the entire nuclear command and control system knows, holy shit.
Buckminster Fuller has a worldwide patent on his own way of holding shapes together. He is famous for his domes. They've made him $1 million. But at one time or another in the last 40 years, he's made front-page news as an architect, aviator, engineer, a sailor, a scientist, and a philosopher. But he is none of these by profession.
These are what we call geodesic radomes, and they are designed to protect very powerful and important apparatus from the great storms of nature.
Mr. Fuller, I'm sure you're familiar with Thurber, the poet and the cartoonist, James Thurber.
Yeah.
And he has a cartoon called The Last Flower, which is quite popular. Do you know it? It's a picture of a flower, and it says, when all the world wars were over, all that was left was one flower and one man and one woman. And they got together, and they had a family, and then that family had family, and then they created industry, and then they created governments, and then they created armies, and then they had a war, and when it was all over, the last thing that was left was one flower, one man, and one woman. Is there anything in your studies or in your philosophies that points to the fact that this evolutionary process of the world is just one continual cycle of we are here, we are wiped out, a new group comes, and it is wiped out? Or do you believe that we are the group that will continue?
No, I would see the final one flower and the couple, and everything radiation around them, all through. Just like Mars or any other very barren planet.
Salut tout le monde. In today's video I will be continuing to read from Differential Geometry by Erwin Kreyszig. We are currently in Chapter 5, which is on geodesic curvature and geodesics. But today's video is going to begin with a pop quiz of sorts. In fluid dynamics, Bernoulli's principle states that an increase in the speed of a parcel of fluid occurs simultaneously with decrease in either the pressure or the height above a datum. That is, for a steady incompressible fluid flow with the negligible viscous forces, and where v is the fluid flow speed, g is the acceleration of gravity, z is the vertical elevation of the point of fluid, p is the pressure, and rho is the density of the fluid, then a common form of an equation expressing Bernoulli's principle is v squared over 2 plus g times z plus p over rho. The question is, for which of the members of the Bernoulli family is this principle named after? That is, for which Bernoulli do we call this Bernoulli's principle? Johann, Daniel, Nicolaus, or Jacob? That's right, Daniel Bernoulli. And actually, Daniel Bernoulli was known as the ablest of the younger Bernoullis, but it was really his father, Johann Bernoulli, whose scientific achievements we're interested in today. In particular, that Johann Bernoulli solved the problem of the shortest distance between 2 points on a convex surface in 1697, and he showed that the osculating plane of the geodesic line must always be perpendicular to the tangent plane, as we will see later. So I haven't gone to the primary source on this one, but I presume that Johann Bernoulli's solution is the coinage of geodesic as a mathematical term derived from the term geodesy, which is a Middle Latin term from the 1560s, so about a century before Johann Bernoulli, meaning the art of land surveying, and geodesic thus being the shortest route between 2 points on the Earth's surface. If not Johann Bernoulli, then it was perhaps Leonhard Euler, who after all was educated by Johann Bernoulli, who first coined geodesic for mathematics. Euler was an acquaintance of Daniel Bernoulli, like the Bernoulli's principle, Daniel Bernoulli, and Euler himself came up with the actual equation formulas, not only for the Bernoulli principle mentioned earlier, but Euler also obtained the equation of geodesics for implicit surfaces, of course, among the many, many other things that Euler did. The word geodesic in math also commonly appears in the term geodesic curvature, which according to the Kreyszig book was due to Joseph Louisville in 1850. And I personally first heard of Joseph Louisville with the Sturm-Liouville problems and so-called Sturm-Liouville theory in PDEs, or partial differential equations. Some would say that Louisville's most significant contribution to mathematics concerns the theory of algebraic equations and group theory, which he sort of facilitated those ideas to get out there because they were from the posthumous works of Galois following the young mathematician's tragic death. In the case of geodesic curvature, however, Louisville was publishing the 5th edition of a man named Gaspard Monge's work titled Application d'analyse à la géométrie. Not only did he add to it Gauss's famous memoir, Disquisitiones generales circa superficie curvas. I'm assuming that means general disquisitions on the topic of superficial curves. But he also appended important related notes of his own, including the introduction of the notions of geodesic curvature of curves on a surface and the integration of the equation of geodesic lines. It is of note that Gaspard Monge is known as the father of differential geometry for his work Application d'analyse à la géométrie. Sorry, my French pronunciation of that title was pretty awful both times, I'm sorry. Geodesics are very useful indeed, as the shortest path problem is very active among the robot motion planning and terrain navigation communities, from what I've gathered, where surfaces are represented as polyhedral surfaces and their problem is solved using computational geometry techniques. I'm sure you've seen a geodesic dome before, and typically these approximately spherical enclosures of space are a surface of polyhedra. Typically these polyhedra are triangles, but geodesic domes are also thought to be based on the shape of what's known as a truncated icosahedron, which an icosahedron is a platonic solid, but a truncated icosahedron is an Archimedean solid, and between the Archimedean solids, the platonic solids, which in a previous video I mentioned that platonic solids might as well be called Pythagorean solids for all we know, or Timaeus solids, but that's a whole other story. But between the Archimedean solids, the platonic solids, and then a few other things, those are all under the family of convex polyhedra in general, okay? So a truncated icosahedron as well as an icosahedron are both convex polyhedra, but the truncated icosahedron is an Archimedean solid and the icosahedron is a platonic solid. The icosahedron, if I'm not mistaken, is 20 faces and each face is a triangle. I have a so-called Rubik's Cube family twisty puzzle that is an icosahedron shape, but the way that the net on the surface is cut, basically, the net I'm referring to as, like, think of the coordinate system on the surface of it, it has caused for there to be these little tiny pieces where the way that you turn the face on the icosahedron shaped twisty puzzle, that little tiny piece broke on like the first time that I turned that puzzle, and so I don't use it, and I can't find another icosahedron shaped twisty puzzle besides the one that's cut the same way as that one that breaks. But the truncated icosahedron is composed of hexagon and pentagon faces and is actually in the shape of a football, or as we would call in America, a soccer ball. Coincidentally, there's this whole other chemical structure called a buckyball or fullerene, which I believe fullerene is a family of, you could call it geodesic dome-shaped chemical structures, and the one that's composed of 20 elements of carbon is called like Buckminster Fullerene or something like that. But I don't know anything about chemistry. The first geodesic dome was officially designed by a German named Walter Bauersfeld, which was constructed in 1922. 30 years later, however, as I kind of alluded with the chemistry stuff, Buckminster Fuller is credited with the popularization of the idea, which he patented in the US in 1954. Geodesic domes appealed to Fuller for various reasons, such as that their geometric surface distributes stress well throughout the structure, making them able to withstand heavy loads for their size and thus a very inherently stable structure, as well as because the shape of a sphere encloses the greatest volume for the least surface area. So with these factors in mind, the idea that we make buildings the way that we do instead of living in a society of geodesic domes, to Fuller, that seems like a suboptimal use of building materials, and that if we did inhabit geodesic domes entirely instead, then we would have more buildings and or more available indoor room and or more efficient use of building resources.
I learned, for instance, as you can, that the Earth is not touching the moon is not touching the sun, and so forth, yet we all held together this invisible gravity that Kepler discovered. And yet we were making all of our buildings brick on brick, compression to compression. Found out then how then to enclose space. So I found then when you do that, you don't have to have all these columns and beams. You have absolutely clear span of space, absolutely unlimited. By virtue of this, all the geodesic domes are made on this principle, and we'll find that I have them. There are now over 300,000 geodesic domes around the world, and they're enclosing space with so little that using the principles of
and this is more philosophy for human evolution.
It's about everything. It's about speculative history of why we're here on the planet, the kind of thing they've been talking to you about from yesterday to today.
Well, as I sit and listen to you, I understand how you got those 48 honorary doctorate degrees.
Already in reading this differential geometry book, comments from viewers like you have referred to geodesics. In modern physics, involutes are relevant in the study of space-time curvature, as they can help describe the behavior of geodesics near curved surfaces or gravitational sources. Another one, regarding the completeness of metric spaces, completeness ensures the existence and uniqueness of geodesics, which are curves that locally minimize distance. A spoiler that is relevant for today's differential geometry reading stream. Geodesics are curves that locally minimize distance and can be understood in terms of their tangent vectors. The behavior of geodesics is closely related to properties of tangent vectors and their transformations. Here's another one. Compactness allows for a more systematic analysis, such as proving the existence of solutions to differential equations and the formulation of theorems. Compactness is crucial to the Gauss-Bonnet theorem, as it relates curvature and topology. While the Gauss-Bonnet theorem deals specifically with Gaussian curvature, the fundamental theorems of vector calculus, such as Green's theorem and Stokes' theorem, address integral theorems. Despite operating in different contexts, there are insights into their relationship. That last one isn't about geodesics specifically, but it refers to the Gauss-Bonnet theorem, which is in this chapter, so I figured I'd include that one. And speaking of the Gauss-Bonnet theorem, this theorem, alongside the Theorema egregium, the remarkable theorem by Gauss, are considered two of the big theorems historically at this level of differential geometry, if you want to call it that. The Gauss-Bonnet theorem was actually briefly alluded to in the preface to the Kreyszig book, where it says that, per the name differential, most of the topics covered will be on the so-called local scale. But the preface qualified this by saying that there would be a few instances where global or so-called in the large properties would be investigated, and the Gauss-Bonnet theorem is one such notion of differential geometry in the large. And I also previously mentioned in the intro to my previous episode on lengths, areas, and angles on surfaces that light that is not interfered upon by any other electromagnetic wave is a geodesic in space-time. Anyways, without any further ado, let's get into the reading. Chapter 5, Geodesic Curvature and Geodesics. Section 49, Geodesic Curvature. We now will ask for a shortest arc on a surface, capital S, joining two arbitrary fixed points, capital P1 and capital P2. Of course, there exist infinitely many arcs on capital S with endpoints capital P1 and capital P2. The question is whether this set of arcs includes an arc capital C of minimum length and what conditions capital C must satisfy in order to be the shortest of all those arcs. Obviously, this is a problem of calculus of variation. It was first considered by Johann Bernoulli in 1697. The problem becomes very simple if capital S is a plane. In this case, a uniquely determined shortest arc joining P1 and P2 exists, namely the segment of a straight line which has the endpoints P1 and P2. On an arbitrary surface, the curves of minimal length will play a role similar to that of straight lines in a plane. Straight lines can be characterized by the property that their curvature vanishes identically. We first introduced the fundamental concept of geodesic curvature, kappa sub g of a curve on a surface. In the following section, we will study curves whose geodesic curvature vanishes identically. These curves are called geodesics. In section 51, we shall prove that an arc of minimum length must necessarily be an arc of a geodesic. Finally, we shall obtain sufficient conditions which must be satisfied in order that an arc capital C be the shortest of all arcs which join two given points P1 and P2 on a surface and lie in a neighborhood of C. We will now define the concept of geodesic curvature, kappa sub g of a curve capital C on a surface capital S whose vector parametric representation x in terms of u1 and u2 is of class r greater than or equal to 2. We assume that capital C is given by a parametric representation where u1 is equal to a function u1 in terms of s, and u2 is also given in terms of a function called u2 in terms of s, where s is the arc length of capital C. Let capital P be an arbitrary point of capital C. We denote by capital C prime the orthogonal projection of capital C on the tangent plane capital E of capital P to capital S at capital P, for which refer to figure 57. The geodesic curvature kappa sub g of capital C at capital P is defined as the curvature of the projected curve capital C prime at capital P taken with a suitable sign. The sign of kappa sub g is defined as follows. Suppose that the curvature of capital C prime at capital P is not 0. Then kappa sub g has a positive sign if the center of curvature of capital C prime at capital P lies in the direction of the unit vector E equals the cross product of n with t, where n is the unit normal vector to capital S at capital P and t is the unit tangent vector to capital C at capital P. Kappa sub g has a negative sign if that center of curvature lies in the direction opposite to the vector E. The sign of kappa sub g thus depends on the orientations of capital S and capital C. In figure 57, kappa sub g is negative. The name geodesic curvature was introduced by Louisville in 1850. According to the relation kappa times cosine of gamma equals kappa sub n, where kappa sub n, when a fixed tangent direction has been chosen on a surface at a particular point, is a constant, the normal curvature kappa sub n of capital S at capital P in the direction of capital C is given by kappa sub n equals kappa times cosine gamma, where gamma is the angle between the unit normal vector n to capital S and the unit principal normal vector P to capital C at capital P. We now consider the cylinder capital Z, which projects the curve capital C orthogonally on capital E of capital P. The generating lines of capital Z have the direction of n. The normal to capital Z at capital P has the direction of E. Capital Z intersects capital E of capital P, referring to the tangent plane, not the vector E that was just mentioned, orthogonally along capital C prime. Hence, the curvature of capital C prime at capital P, which by definition is the magnitude of kappa sub g, is the normal curvature of capital Z at capital P in the direction of the unit tangent vector T to capital C. In consequence of kappa sub n equals kappa times cosine of gamma, we therefore have the magnitude of kappa sub g is equal to kappa times sine of gamma. We may represent the curvature vector k equals kappa times p of capital C at capital P as a sum of the normal curvature vector k sub n equals kappa sub n times n, for which refer back to section 39, and of the geodesic curvature vector k sub g equals kappa sub g times e, and k equals k sub n plus k sub g, which equals kappa sub n times n plus kappa sub g times e. If we take the scalar product of the previous relation and e, then in consequence of e equals n cross t, we find that the scalar product of e with k, that is e dot k, equals the dot product of e and t dot, or the first derivative of the tangent vector in terms of arc length. The scalar product of e with t dot equals the scalar product of the result of n cross t with t dot. This equals a determinant which column-wise is the vectors t, then t dot, then n, and this is equal to kappa sub g. Or kappa sub g equals the determinant column-wise vectors x dot, then x double dot, then n. Clearly, in general, the geodesic curvature kappa sub g depends not only on the curve capital C, but also on the surface capital S on which capital C lies, except for the case when t dot equals x double dot equals 0, and therefore kappa sub g equals 0. Thus, a circle capital C of radius r, when considered as a great circle on a sphere, has kappa sub g equals 0, since in this case the vectors t, t dot, and n lie in a plane through the center of the sphere. If, however, capital C lies in a plane, then the magnitude of kappa sub g is equal to kappa, which is equal to 1 over r. There's a fundamental contrast between the normal curvature, kappa sub n, and the geodesic curvature, kappa sub g. While kappa sub n depends on both fundamental forms, kappa sub g depends on the first one only. Theorem 49.1. The geodesic curvature kappa sub g of a curve capital C on a surface capital S depends on the first fundamental form of S only, and also, of course, on capital C. The proof is as follows. We have to find a representation of kappa sub g in terms of functions of the coefficients g sub alpha beta of the first fundamental form. Of course, quantities which depend on the curve capital C will also occur in this representation. If we differentiate x dot equals x sub alpha times u alpha dot with respect to the arc length S of capital C, we obtain x double dot equals x sub beta gamma times u beta dot times u gamma dot plus x sub epsilon times u epsilon double dot. From this, by the formulae of Gauss, we find that the cross product of x dot with x double dot is equal to x sub alpha times u alpha dot cross with the quantity, inner quantity, Christoffel sub beta gamma superscript epsilon times u beta dot times u gamma dot plus u epsilon double dot closed inner quantity times x sub epsilon plus b sub beta gamma times n times u beta dot times u gamma dot closed quantity. We have that x sub 1 cross x sub 2 is equal to the square root of g times n, and that x sub 2 cross x sub 1 equals the negative square root of g times n, for which refer to the previously given expression for the unit normal vector to a surface at a given point, which is n equals x1 cross x2 over the positive square root of g. Furthermore, since x sub alpha cross x sub alpha equals 0 and n cross n equals 0, and the scalar product of n with itself is equal to 1, we finally obtain kappa sub g equals the result of the cross product of x dot with x double dot, then scalar product with n, which is equal to the square root of g times the quantity Christoffel sub beta gamma superscript 2 times u1 dot times u beta dot times u gamma dot plus u1 dot times u2 double dot minus Christoffel sub beta gamma superscript 1 times u2 dot times u beta dot times u gamma dot minus u2 dot times u1 double dot closed quantity. Or kappa sub g equals the square root of g times the quantity Christoffel sub 1 superscript 2 times the cube of u1 dot plus quantity 2 times Christoffel sub 1 2 superscript 2 minus Christoffel sub 1 superscript 1 closed quantity times the square of u1 dot times u2 dot minus quantity 2 times Christoffel sub 1 2 superscript 1 minus Christoffel sub 2 2 superscript 2 closed quantity times u1 dot times the square of u2 dot minus Christoffel sub 2 2 superscript 1 times the cube of u2 dot plus u1 dot times u2 dot plus u1 dot times u2 double dot minus u1 double dot times u2 dot closed quantity, and this completes the proof. In the last expression given in the proof for kappa sub g, we may easily replace the arc length s by any allowable parameter t. Denoting by primes the derivatives with respect to t, we have u1 dot times u2 double dot minus u1 double dot times u2 dot. This equals the quantity u1 prime times u2 double prime minus u1 double prime times u2 prime closed quantity times t dot cubed. Analogously, in terms of that same second given expression for kappa sub g from the proof, if all terms of that expression are multiplied by t dot cubed, we therefore have a common factor t dot cubed on the right hand side of that expression for kappa sub g, and have just to replace the dots by primes. We apply that same expression for kappa sub g to the coordinate curves. On the curves u1 equal to a constant, we have that u1 dot equals 0 and u2 dot equals 1 over the square root of g sub 2. We thus obtain that the quantity kappa sub g closed quantity with the subscript u1, where u1 is equal to a constant as that subscript, then this expression for this particular kappa sub g sub constant u1 is then equal to negative Christoffel symbol sub 2 superscript 1, then times the square root of g over g sub 2 to the power of 3/2. Analogously, the geodesic curvature of the curves u2 equal to a constant is given by the expression quantity kappa sub g closed quantity subscript u2 equal to a constant is then equal to Christoffel sub 1 superscript 2 times the square root of g over g sub 1 to the power of 3/2. If in particular the coordinates u1 and u2 are orthogonal, then by the previously given formulae for Christoffel symbols, we have that Christoffel sub 2 superscript 1 is equal to negative 1 over 2 times g sub 1 then times partial g sub 2 partial u1, and Christoffel sub 1 superscript 2 is equal to negative 1 over 2 times g sub 2 then times partial g sub 1 partial u2. And therefore in this case we have for A that the quantity kappa sub g closed quantity subscript constant u1, this is equal to 1 over the quantity 2 times g sub 2 times the square root of g sub 1 closed quantity, then times partial g sub 2 partial u1, which is equal to 1 over the square root of g sub 1, then times the partial derivative with respect to u1 of the logarithm of the square root of g sub 2. And we also have for B that the quantity kappa sub g closed quantity with the subscript constant u2 is equal to negative 1 over the quantity 2 times g sub 1 times the square root of g sub 2 closed quantity, then times partial g sub 1 partial u2. This is then equal to negative 1 over the square root of g sub 2, then times the partial with respect to u2 of the logarithm of the square root of g sub 1. And in either of these cases, g sub 12 is equal to 0. Section 50, Geodesics. A curve capital C on a surface capital S is called a geodesic curve or geodesic if its geodesic curvature kappa sub g vanishes identically. Theorem 50.1. Straight lines on any surface are geodesics. A curve capital C of class R greater than or equal to 2, not a straight line, is a geodesic on a surface capital S if and only if at each point of capital C at which the curvature kappa of capital C is not 0, the unit normal vector n to capital S lies in the osculating plane capital O of capital C. The proof is as follows. We use the relation that the magnitude of kappa sub g equals kappa times sine of gamma. At points of capital C at which kappa equals 0, also kappa sub g equals 0. At any other point we have, if n lies in capital O, then n and p lie in the same line and therefore kappa sub g vanishes. Refer to the relation for the magnitude of kappa sub g previously mentioned. Conversely, if kappa sub g equals 0, then in consequence of that relation for the magnitude of kappa sub g, either kappa must vanish or gamma must have the values 0 or 2 pi. That is, n must lie in the osculating plane capital O of capital C. Along an asymptotic curve capital A on a surface capital S, the osculating planes of capital A and the tangent planes to capital S coincide, while at any point of a geodesic on capital S, those planes are orthogonal to each other. Furthermore, at any point of an asymptotic curve capital A, the normal curvature kappa sub n of the surface in the direction of capital A vanishes, while at any point of a geodesic, its geodesic curvature kappa sub g is 0. In the case of an asymptotic curve, we have the magnitude of kappa sub g is equal to kappa, for which refer to the relation for the geodesic curvature vector k equals k sub n plus k sub g, which is equal to kappa sub n times n plus kappa sub g times e. Let us now consider the differential equation of the geodesics. Kappa sub g equals 0, somewhat more in detail. Introducing into the second relation for kappa sub g from the proof of theorem 49.1, introducing into that relation u1 as a parameter, we have that u1 dot times u2 double dot minus u1 double dot times u2 dot is equal to d squared u2 du1 squared times the cube of u1 dot. And the differential equation of the geodesics kappa sub g equals 0 therefore takes the form d squared u2 du1 squared minus Christoffel sub 22 superscript 1 times the cube of du2 du1, then minus the quantity 2 times Christoffel sub 12 superscript 1 minus Christoffel sub 22 superscript 2 closed quantity times the square of du2 du1, then plus the quantity 2 times Christoffel sub 12 superscript 2 minus Christoffel sub 11 superscript 1 closed quantity, then times du2 du1 plus Christoffel sub 11 superscript 2, all equal to 0. This differential equation of second order is of the form d squared u2 du1 squared equal to a function h in terms of u1, u2, and du2 du1. If we assume that the representations of the surface capital S and of the curve on capital S under consideration are of class r greater than or equal to 3, then this function h is a function of class r minus 2 greater than or equal to 1, and the differential equation of the geodesics kappa sub g equal to 0 originally has exactly one solution satisfying certain given initial conditions, namely u2 of u1 naught, which is equal to u2 naught, and du2 du1 evaluated at u1 equal to u1 naught being then equal to, let's say, du2 du1 naught. So the entire quantity du2 du1 itself has a subscript 0. This means that at any point capital P on a surface capital S, there is exactly one geodesic passing through capital P in a given direction. Furthermore, as will be seen in future section 53, there is exactly one geodesic through two given points of a sufficiently small portion of a surface. In the large, the latter property is true for the plane, but not in general. Thus, on a sphere, there are infinitely many great circles through two diametrically opposite points. On a cylinder of revolution, the generating straight lines, circles, and circular helices are geodesics. Consequently, for two given points, capital P and capital Q, not on the same circle, there are infinitely many helices through capital P and capital Q. From the relations for geodesic curvature when U1 and U2 are constants respectively, we immediately obtain Theorem 50.2. The coordinate curves where u1 are constant and u2 are constant on a portion of a surface, capital S, whose vector parametric representation x in terms of u1 and u2 of class r greater than or equal to 2, are geodesics if and only if Christoffel sub 22 superscript 1 equals 0 and Christoffel sub 11 superscript 2 equals 0 respectively. For example, in the parametric representation of a sphere in what you might call cylindrical coordinates that was previously given in section 25, we have that representation being namely x of u1 and u2 equal to entry-wise r cosine u2 times cosine u1, and then r times cosine u2 times sine u1, and then r times sine u2. We have that the coordinates u1 and u2 are orthogonal. We have g sub 11 equals r squared times cosine squared of u2, and g sub 22 equals r squared, and partial g sub 22 partial u1 equals 0. Therefore, Christoffel sub 22 superscript 1 equals 0, for which we can refer back to the previous formulae for the Christoffel symbols. That is, the curves where u1 is a constant are geodesics. Furthermore, partial g sub 11 partial u2 equals negative 2 times r squared times cosine of u2 times sine of u2. This expression vanishes if u2 equals 0, that is, Christoffel sub 11 superscript 2 equals 0, along the equator, which is the only geodesic of the curves where u2 equals a constant. At the poles, u2 equals positive or negative pi over 2, and also Christoffel sub 11 superscript 2 equals 0. But the formulae for the representation of the sphere is not valid at these points. Furthermore, we see for the expressions for the geodesic curvature when u1 and u2 are orthogonal and each are constants, that the coordinate curves of orthogonal coordinates are geodesics if and only if g sub 1 does not depend on u2 and g sub 2 does not depend on u1. Finally, we mention an important application of Theorem 50.1. Let us determine the torsion tau of s of a geodesic capital G with a vector parametric representation x of s, which is not a straight line, on a surface capital S with a vector parametric representation x in terms of u1 and u2 in Euclidean space R3, where lowercase s denotes the arc length of capital G. According to Theorem 50.1, the principal normal of capital G and the normal of capital S coincide. If we choose a suitable orientation of the unit normal vector n of capital S, we thus have that the vectors p and n are equal to each other, where p is the unit principal normal vector of capital G. Hence, capital G, this geodesic, has the unit binormal vector b, which is equal to the cross product of x dot with p, which is equal to x dot cross n. By the formulae of Frenet, we thus obtain that b dot is equal to negative tau times p, which is equal to negative tau times n, which is equal to x double dot cross n plus x dot cross n dot. Since x double dot and n are parallel vectors, the first of the two vector products vanishes. Hence, tau times n equals n dot cross x dot. If we take the scalar product of this relation for tau times n and n, we thus find that tau is equal to the discriminant whose columns are the vectors n dot, and x dot respectively. Obviously, this expression for the torsion of a geodesic capital G at a point capital P of capital S depends only on capital P and on the direction of the tangent to capital G at capital P. We may thus define the geodesic torsion of a curve capital C on the surface capital S at a point capital P is the torsion of the geodesic through capital P which touches capital C at capital P. The geodesic torsion is thus given by the previous relation for tau as the discriminant of n dot and x dot, and will be obtained by tau sub g. From the relation for geodesic torsion and Theorem 45.1, which gives a relation for displacement in a principal direction, namely kappa sub n times dx plus dn equals 0, we thus obtain Theorem 50.3. The geodesic torsion of a line of curvature vanishes identically. Furthermore, we have Theorem 50.4. If a geodesic capital G on a surface capital S is a line of curvature on capital S, then G is a plane curve. Every plane geodesic on a surface capital S is a line of curvature on capital S. A relation between the geodesic torsion tau sub G and the torsion tau of a curve on a surface will be derived in section 88. Problem 50.1. Determine the geodesics of the plane by means of the way of writing the differential equation of the geodesics in terms of derivatives du2, du1, as well as Christoffel symbols, which was previously given. We choose Cartesian coordinates in the plane. Then all Christoffel symbols vanish, and the differential equation for the geodesics reduces to du2 squared du1 squared equals 0. Integrating twice, we have u2 equals a times u1 plus c. This is a representation of a straight line. Problem 50.2. Prove that any circular helix capital C on a cylinder of revolution capital S is a geodesic on capital S. Let the vector x in terms of t equal entry-wise to r cosine t, then r sine t, then ct, be any circular helix on a cylinder of revolution, x in terms of u1 and u2, entry-wise given by r cosine u1, r sine u1, and then u2. The vector x double prime equal to entry-wise negative r cosine t, then negative r sine t, then 0, lies in the osculating plane, for which you can refer to the equation for the osculating plane, which is in section 11. The unit normal vector n, which is equal entry-wise to cosine u1, then sine u1, then 0, to the cylinder, for which we can refer again back to the equation for the unit normal vector to capital S at capital P, n equals x1 cross x2 over the positive square root of g. This unit normal vector n to the cylinder lies also in the corresponding osculating plane of the helix. Hence, helices are geodesics of the cylinder, and refer back to Theorem 50.1. Section 51. arcs of minimum length. Let capital P1 and capital P2 be any two fixed points on a surface, capital S, with the vector parametric representation x in terms of u1 and u2, which is of class r greater than or equal to 2. We assume that there exists an arc of class r tilde, which is greater than or equal to 2, and capital C given by u1, which is equal to a function capital F1 of t, and u2, which is equal to a function capital F2 of t, where the parameter t is greater than or equal to t1 and less than or equal to t2, with endpoints capital P1 and capital P2, such that capital C has minimum length among all arcs given capital C star in terms of u1, which is equal to a function capital F1 star in terms of t, and u2, which is equal to a function capital F2 star in terms of t, where this parameter t likewise is greater than or equal to t1 and less than or equal to t2. All of these arcs capital C star on capital S, which join capital P1 and capital P2 and lie in a neighborhood of capital C. We will prove that capital C must be an arc of a geodesic. We set capital Fi star of t equal to capital Fi of t plus epsilon times v superscript I of t, where v superscript I of t1 equals v superscript I of t2, which equals 0 for I equal to 1 or 2, where the magnitude of epsilon is sufficiently small. Furthermore, we assume that any function of t occurring is of class r star, which is greater than or equal to 2. According to the previously given relation for the length of an arc on a surface from section 35, which is s equals the integral from t0 to t1 of the square root of the quantity g sub alpha beta times u alpha prime times u beta prime closed quantity. S equals the integral from t0 to t1 of the square root of the quantity g sub alpha beta times u alpha prime times u beta prime closed quantity dt. According to this, capital C has the length, lowercase s in terms of capital C, equal to the integral from t1 to t2 of the function h in terms of capital F1, capital F2, capital F1 prime, and capital F2 prime, then the integral in terms dt, where this function h equals the square root of the quantity g sub alpha beta times capital F alpha prime times capital F beta prime closed quantity, and as per the usual convention, primes here denote derivatives with respect to the parameter t. Capital C star has the length, lowercase s in terms of capital C star equals lowercase s of epsilon, which is equal to the integral from t1 to t2 of the function h of capital F1 star, capital F2 star, capital F1 star prime, and capital F2 star prime, and the integral is all then dt. We have that s of 0 is equal to s of capital C. In order that s of epsilon have an extreme value for epsilon equals 0, we must necessarily have that ds d epsilon evaluated at epsilon equals 0 is equal to 0. Now, ds d epsilon itself is equal to the integral from t1 to t2 of partial h, partial capital F I star, then times partial capital F I star, partial epsilon, plus partial h, partial capital F I star prime, then times partial capital F I star prime partial epsilon, with the entire integral with respect to dt. And therefore, for what we previously set for capital F I star of t and vi of t1 and vi of t2, we have that ds d epsilon evaluated at epsilon equals 0 equals the integral from t1 to t2 of partial h partial capital Fi, then times vi, plus partial h partial capital Fi prime, then times vi prime, with the entire integral then dt. Integration by parts yields the integral from t1 to t2 of partial h partial capital Fi prime, then times vi prime dt equals partial h partial capital Fi prime, then times vi, with a lower evaluation at t1 and an upper evaluation at t, then minus the integral from t1 to t2 of ddt of partial h partial capital Fi prime, then times vi dt. Since vi of t1 equals vi of t2, which equals 0, the first term on the right hand side vanishes. We thus obtain that ds d epsilon evaluated at epsilon equals 0 is equal to the integral from t1 to t2 of the quantity partial h partial capital Fi minus ddt of partial h partial capital Fi prime closed quantity times vi then dt. Since capital C is assumed to have minimum length compared with all neighboring arcs, that is, since the preceding integral must vanish for any pair of functions vi which vanish finish at T1 and T2, we must have that partial h partial capital Fi minus ddt of partial h partial capital Fi prime is then equal to 0, where I can be 1 or 2, where h is defined by h equals the square root of the quantity g sub alpha beta times capital F alpha prime times capital F beta prime closed quantity. The previously given equations are called the Euler-Lagrange equations of the variational problem under consideration. These equations must necessarily be satisfied in order that capital C, given in u1 by the function capital F1 of t and in u2 by capital F2 of t, compared with any above arc capital C star in a neighborhood of capital C, has minimum length. We will now insert the function h into the Euler-Lagrange equations. Instead of capital Fi of t, we may simply write ui of t. We have that partial h partial u mu equals 1 over the denominator 2 times the square root of the quantity g sub alpha beta times u alpha prime times u beta prime closed quantity, then times partial g sub mu sigma partial u mu times u nu prime times u sigma prime. This all equals 1 over 2s prime, then times partial g sub nu sigma partial u mu times u nu prime times u sigma prime. And partial h partial u mu prime equals a fraction with a numerator of 2 times g sub mu nu times u nu prime over a denominator of 2 times the square root of the quantity g sub alpha beta times u alpha prime times u beta prime closed quantity. This fraction is then equal to 1 over s prime, then times g sub mu nu times u nu prime. Therefore, ddt of partial h partial u mu prime equals negative s double prime over s prime squared, then times g sub mu nu, then times u nu prime, plus 1 over s prime times the quantity partial g sub mu nu partial u sigma times u nu prime u sigma prime plus g sub mu nu times u nu double prime closed quantity. The Euler-Lagrange equations thus take the form 1/2 partial g sub mu sigma partial u mu times u nu prime u sigma prime plus s double prime over s prime times g sub mu nu times u nu prime minus partial g sub mu nu partial u sigma times u nu prime times u sigma prime minus g sub mu nu times u nu double prime equals 0. Using the symmetry for the Christoffel symbols with respect to the first two indices, as well as the representation for the first partial derivatives of the coefficients g sub alpha beta of the first fundamental form represented as a sum of two Christoffel symbols of the first kind as previously given in section 47, and partial g sub mu nu partial u sigma times u nu prime u sigma prime equals 1/2 times the quantity partial g sub mu sigma partial u nu times u sigma prime times u nu prime plus partial g sub mu nu partial u sigma times u nu prime times u sigma prime closed quantity, we obtain from this that s double prime over s prime times g sub mu nu times u nu prime minus Christoffel sub mu sigma mu times u nu prime times u sigma prime minus g sub mu nu times u nu double prime equals 0. Taking the inner product of this expression and g superscript mu tau, we have that s double prime over s prime times u tau prime minus Christoffel sub mu sigma superscript tau times u nu prime times u sigma prime minus u tau double prime equals 0. If we introduce the arc length lowercase s of capital C as a parameter then since s dot equals 1 and s double dot equals 0, the Euler-Lagrange equations as previously given take the form u tau double dot plus Christoffel sub mu sigma superscript tau times u nu dot times u sigma dot equals 0, where tau can be 1 or 2. We will prove that this relation is equivalent to kappa sub g equal to the discriminant column-wise the vectors x dot, x double dot, and then n, which is then equal to 0, for which referred to the previously given relation for kappa sub g as a discriminant similarly from section 49. We have that x dot equals x sub tau times u tau dot, and that x double dot equals x sub tau, then times the quantity Christoffel sub mu sigma superscript tau times u nu dot times u sigma dot plus u tau double dot closed quantity plus vector n times b sub nu sigma, then times u nu dot times u sigma dot, for which refer back to the previously given expansion of x dot cross x double dot given in section 49. Because of this form of the Euler-Lagrange equations that we're working with, the expression in brackets vanishes in the previous expression for x double dot. That is, x double dot and n are collinear. Consequently, the determinant of vectors x dot, x double dot, and n is equal to 0. We prove the converse, starting from the assumption that this determinant of x dot, x double dot, and n equals 0. Since x dot and x double dot as well as x dot and n are linearly independent, that determinant vanishes if and only if x double dot and n are linearly dependent. That is, in the previously given relation for x double dot, the expression in brackets must vanish. Consequently, the intended form of the Euler-Lagrange equations that we want must hold. We sum up our result as follows. Theorem 51.1. In order that an arc capital C of class R greater than or equal to 2 on a surface capital S with a vector parametric representation x in terms of u1 and u2 with endpoints capital P1 and capital P2 have minimum length among all neighboring arcs on capital S which join capital P1 and capital P2, capital C must necessarily satisfy the Euler-Lagrange equations u tau double dot plus Christoffel sub nu sigma superscript tau times u nu dot times u sigma dot equals 0. These equations are satisfied if and only if capital C is an arc of a geodesic on capital S. In the case of a plane, the condition that capital C be an arc of a geodesic is also sufficient. Indeed, in this case, straight lines are the only geodesics, and any segment capital P1 and capital P2 is the arc of minimum length joining its endpoints capital P1 and capital P2. The fact that the above condition cannot be sufficient in the case of any surface may be illustrated, for instance, on a sphere capital S. There is exactly one great circle capital G on capital S passing through two given points capital P1 and capital P2 not diametrically opposite. But at most one of the two arcs of capital G with endpoints capital P1 and capital P2 can be an arc of minimum length joining capital P1 and capital P2. A sufficient condition for an arc capital C to be an arc of minimum length will be stated in the following section. Problem 51.1. Determine the solution of the first of the differential equations of the Euler-Lagrange equations in the case of a surface of revolution capital S and prove that the meridians of capital S are always geodesics. Cylinders of revolution have been considered just before. Any other surface of revolution can be locally represented in the form vector x in terms of u1 and u2, which entry-wise is u2 times cosine u1 and then u2 times sine u1 and then a function h in terms of u2. We thus obtain that g sub 11 is equal to u2 squared, g sub 12 is equal to 0, g sub 22 is equal to 1 plus h prime squared, where a prime denotes the derivative with respect to u2. Furthermore, Christoffel sub 12 superscript 1, which is equal to Christoffel sub 21 superscript 1, is then equal to 1 over u2. All other Christoffel symbols with the superscript 1 vanish. The first of the two equations of the Euler-Lagrange equations thus takes the form u1 double dot plus 2 over u2 times u1 dot times u2 dot equals 0, or u1 double dot over u1 dot equals negative 2 times u2 dot over u2. Integrating once, we have that log of u1 dot equals negative 2 times log of u2, then plus c star, or u1 dot equals c over u2 squared, where c star and c are constants. From this we obtain that du1 squared equals c squared over u2 to the fourth, then times ds squared, which is then equal to c squared over u2 to the fourth, then times the quantity u2 squared times du1 squared plus inner quantity 1 plus h prime squared closed inner quantity times du2 squared closed quantity. Integrating once more, we have that u1 is equal to positive or negative c times the integral of the square root of a fraction with a numerator 1 plus h prime squared all over a denominator of u2 to the fourth minus c squared times u2 squared, and this integral is all du2. Setting c equal to 0, we have u1 equals 0. That is, the meridian u1 equals 0 is a geodesic. Hence, all meridians are geodesics. Section 52. Geodesic parallel coordinates. A one-parameter family of geodesics on a surface capital S is said to be a field of geodesics in a portion capital S prime of capital S if through every point of capital S prime, there passes just once exactly one of those geodesics. The name field of geodesics was introduced by Weierstrass. For example, a family of parallel straight lines is a field of geodesics in a plane. A pencil of straight lines through a point capital P of a plane capital E is a field of geodesics in any portion of capital E which does not contain the point capital P. There does not exist a field of geodesics on the whole sphere, since any two geodesics, great circles, intersect each other. The generating straight lines of a cylinder capital Z constitute a field of geodesics on capital Z. We may introduce coordinates u1 star and u2 star on a sufficiently small portion capital S of a surface in the following manner. We choose a field of geodesics on capital S as coordinate curves u2 star equal to a constant and their orthogonal trajectories as coordinate curves u1 star equal to a constant. These orthogonal coordinates are called geodesic parallel coordinates. That we obtain an allowable coordinate system on capital S by the above procedure will be seen in connection with forthcoming theorem 52.1. Since the coordinates u1 star and u2 star are orthogonal, we have that g sub 1 2 star equals 0. Since the curves u2 star equal to a constant are geodesics, namely that the geodesic curvature kappa sub g is equal to 0, in consequence of the previously given relations for geodesic curvature for orthogonal u1 and u2 that are also respectively constants, we have that partial g sub 1 1 star partial u2 star equals 0. That is, g sub 1 1 star depends on u1 star only. We set u1 equal to the integral from 0 to u1 star of the square root of g sub 1 1 star, with the integral then being du1 star and u2 equal to u2 star. This transformation leaves the curves u2 star equal to a constant unchanged, and therefore also their orthogonal trajectories. Of course, the corresponding values u1 star equal to a constant will be transformed into other values u1 equal to a constant. The first fundamental form corresponding to the coordinates u1 and u2 is given by the expression ds squared equals du1 squared plus g sub 2 of u1 and u2, that is coefficient g sub 2 from the first fundamental form of u1 and u2, then times du2 squared, which is characteristic for geodesic coordinates. Since in this case g sub 2 equals g, which I believe refers to the discriminant of the first fundamental form, lowercase g refers to, that is, we may write simply ds squared equals du1 squared plus g times du2 squared. If the first fundamental form is given by such a relation for ds squared, the formula for the Gaussian curvature becomes very simple. We then obtain from the equation of Gauss, capital K equals -1 over the square root of g sub 2 then times partial squared square root of g sub 2 partial u1 squared, which is then equal to 1 over 4 times g sub 2 squared, then times partial g sub 2 partial u1 squared, the entire first order derivative, then minus 1 over 2 times g sub 2 then times partial squared g sub 2 partial u1 squared, where that last one is of course a second order partial derivative. Or since g sub 2 equals g, capital K equals -1 over the square root of g, then times partial squared square root of g partial u1 squared. This relation for Gaussian curvature is advantageous, for instance, for the study of surfaces of constant Gaussian curvature, for which refer to section 90 and other purposes. From the expression for the first fundamental form for geodesic coordinates, we obtain the following. Theorem 52.1, which is due to Gauss. Let capital C be any curve on a surface capital S of class r greater than or equal to 3. When sufficiently small, equal lengths are measured from capital C along the geodesics which intersect capital C orthogonally, the locus of their endpoints is an orthogonal trajectory capital C star of those geodesics. Proof. The condition sufficiently small means that we consider the above geodesics only in a neighborhood capital U of capital C where they form a field. The existence of such a neighborhood is an immediate consequence of the fact that the geodesics satisfy the differential equation occurring in the preceding two sections. If we take on capital S coordinates u1 and u2 so that the above geodesics are the curves where u2 equals a constant and their orthogonal trajectories, one of which is capital C, are the curves u1 equal to a constant, then, in consequence of the first fundamental form for geodesic coordinates, the geodesic arcs between any two trajectories, say u1 equal to c1 and u1 equal to C2 have the length given by the integral from C1 to C2 of du1 equal to just C2 minus C1. Since this length is independent of U2, the arcs of all those geodesics between any two of their orthogonal trajectories have the same length. This completes the proof. The curves capital C star defined in Theorem 52.1 are called geodesic parallels of capital C. In consequence of Theorem 52.1, we may introduce geodesic parallel coordinates U1 star and U2 star on a surface capital S as follows. We choose an arbitrary simple curve capital C on capital S to be the coordinate curve U1 star equal to 0. We take the geodesics orthogonal to capital C as coordinate curves U2 star equal to a constant, and finally the geodesic parallels to capital C as curves U1 star equal to a constant. The coordinates thus obtained are allowable in the neighborhood capital U of capital C mentioned in the proof of Theorem 52.1. We are now able to state a sufficient condition which a geodesic arc capital G must satisfy in order that capital G be the arc of minimum length between two given points on a surface. Theorem 52.2. Let capital G be a geodesic arc on a surface capital S with endpoints capital P1 and capital P2. If we can choose a geodesic field capital F on capital S so that capital G becomes an arc of this field and is the only geodesic arc in capital F joining capital P1 and capital P2, then capital G is the arc of minimum length joining capital P1 and capital P2 compared with any other arc which lies entirely in the field capital F and joins capital P1 and capital P2. The proof is as follows. We assume the geodesic parallel coordinates U1 and U2 have been introduced on capital S so that capital G is given by U2 equal to U2 naught, which is equal to a constant. An arbitrary arc with a vector parametric representation x in terms of function U1 of t and U2 of t, where the parameter t is greater than or equal to t1 and less than or equal to t2, which joins capital P1 and capital P2 and lies entirely in the field capital F, has the length lowercase s equals the integral from t1 to t2 of the square root of the quantity u1 prime squared plus g sub 22 times u2 prime squared closed quantity dt, which is greater than or equal to the integral from t1 to t2 of u1 prime dt, which is equal to u1 subscript quantity 2 minus u1 subscript quantity 1. In this expression, the equality sign holds if and only if g sub 22 equals g sub 22 times u2 prime squared equals 0. That is, since g sub 22 is greater than 0, if du2 is equal to 0, then u2 is equal to a constant, and the joining arc is a portion capital G, for which we can refer to figure 58 below. And now an example. 2 points capital P1 and capital P2 on a sphere, not diametrically opposite. Determine a great circle capital G and divide capital G into two arcs. The shorter of these arcs can be embedded in a geodesic field and is therefore the arc of minimum length between capital P1 and capital P2, while the longer of those arcs of capital G cannot be embedded in a geodesic field. See figure 59 above. Geodesic polar coordinates. In the preceding section we considered geodesic parallel coordinates, which are a generalization of orthogonal parallel coordinates in a plane. We will now define geodesic polar coordinates, which are a generalization of plane polar coordinates. Through an arbitrary point capital P of a surface capital S of class r greater than or equal to 3, there passes exactly one geodesic in every direction. We will prove that those geodesics constitute a geodesic field in capital U minus capital P, where capital U is a sufficiently small neighborhood of capital P. For this purpose, we introduce on capital S coordinates U1 tilde and U2 tilde with origin at capital P so that G sub alpha beta tilde equals Kronecker delta sub alpha beta at capital P. Let U alpha tilde equal the function H alpha in terms of S, which S is in terms of C1 and C2, where for U alpha tilde, alpha can be either 1 or 2. And let U alpha tilde then be the solution of the differential equations, namely the Euler-Lagrange equations, which satisfies the conditions that U alpha tilde at 0 equals 0, and U alpha tilde dot at 0 equals C alpha, where alpha can be either 1 or 2. Depending on the choice of C1 and C2, we obtain one of the geodesics through capital P. And capital P always corresponds to lowercase s arc length equals 0. If we set C1 equal to cosine of U2 and C2 equal to sine of U2, then U2 is the angle between that geodesic and the curve U2 tilde equal to 0 at capital P. We have that C1 squared plus C2 squared equals 1, and lowercase s is the arc length of that geodesic. We will prove that for any value values of C1 and C2, the solution, function h alpha of S, where S is in terms of C1 and C2, of the Euler-Lagrange equations can be represented in the form phi alpha in terms of SC1 and SC2, where alpha can be 1 or 2. The transformation S equals KT leaves the form of the Euler-Lagrange equations for this case unaffected. Hence, if the function h alpha in terms of S, in terms of C1 and C2 subsequently, is a solution of these Euler-Lagrange equations, then h alpha of T, which is then of C1 tilde and C2 tilde subsequently, is also a solution of these Euler-Lagrange equations. Since partial U alpha tilde partial T equals partial U alpha tilde partial S times K, or partial U alpha tilde partial T evaluated at T equals 0 equals C alpha times K, where K does not equal 0 and alpha can be either 1 or 2, we have that H alpha in terms of S and subsequently C1 and C2 is equal to a function H alpha in terms of T and subsequently to C1 times K and C2 times K. In particular for T1, we have that the function H alpha in terms of K and subsequently C1 and C2, which is equal to the function HA in terms of L and subsequently C1 times K and C2 times K. Or if we replace K by S, then the function H alpha in terms of S and subsequently C1 and C2 is equal to the function H alpha in terms of L and subsequently C1 times S and C2 times S. Thus we set the function H alpha in terms of L and subsequently C1 times S and C2 times S equal to the function phi alpha in terms of V1 and V2, where in these alpha can be either 1 or 2, and where V alpha equals C alpha times S. By means of the transformation U alpha tilde equal to phi alpha of V1 and V2, where alpha is 1 or 2, then we now introduce V1 and V2 as coordinates on capital S. This transformation is allowable in a sufficiently small neighborhood, capital U of P. Indeed, we have that C alpha is equal to U alpha tilde dot of 0, which is equal to partial H alpha partial S evaluated at S equals 0. And on the other hand, partial H alpha partial S evaluated at S equals 0 equals partial phi alpha partial V gamma times partial V gamma partial S evaluated at V1 equal to V2 equal to 0, which is equal to partial phi alpha partial V gamma times C gamma evaluated at V1 equal to V2 equal to 0. Hence, by comparison, partial phi alpha partial V gamma evaluated at V1 equal to V2 equal to 0 is equal to Kronecker delta sub gamma superscript alpha. Therefore, at capital P, the Jacobian capital J of the transformation has the value 1, and since capital J, the Jacobian, is continuous, it cannot vanish in a certain neighborhood capital U of the point capital P. Furthermore, the coefficients g sub alpha beta star and g sub alpha beta tilde of the first fundamental forms corresponding to v1, v2, and u1 tilde and u2 tilde respectively have at capital P the same values, g sub alpha beta star of 0, 0 equal to Kronecker delta sub alpha beta. v1 and v2 are called Riemann normal coordinates. The geodesics through capital P have the representation v alpha equal to c alpha times s. We now assume that c1 squared plus c2 squared equals 1. Then lowercase s is the arc length of those geodesics. The values of lowercase s, c1, and c2 corresponding to a given point capital Q in terms of v1 and v2, which is not 0, 0, of capital U are uniquely determined. That is, there exists exactly one geodesic joining capital Q and capital P. Hence, the geodesics under consideration constitute a geodesic field in capital U minus capital P. If we write the Euler-Lagrange equations using the coordinates v1 and v2 and insert v alpha equal to c alpha times s, then since v alpha dot equals c alpha and v alpha double dot equals 0, we obtain that Christoffel star sub nu sigma superscript tau times c nu times c sigma equals 0 for tau equal to 1 or 2. Since at capital P these equations must be satisfied for all values of c alpha, all Christoffel symbols, Christoffel star sub nu sigma superscript tau vanish at capital P. Hence all partial derivatives, partial g sub alpha beta star, partial u gamma vanish also at capital P. We set v1 equal to u1 times cosine u2 and v2 equal to u1 times sine u2. The coordinates u1 and u2 thus defined are called geodesic polar coordinates on capital S with the center at capital P, for which refer to figure 60 to the right. Since v1 and v2 are allowable in capital U and the preceding transformation is allowable in capital U minus capital P, the coordinates u1 and u2 are allowable in capital U minus capital P. The coordinate curves u2 equal to a constant are the geodesics through capital P. The corresponding first fundamental form is given by the first fundamental form for geodesic coordinates, the previously given relation ds squared equals du1 squared plus g sub 2 2 in terms of u1 and u2, then times du du2 squared, and the curves u1 equal to a constant are the orthogonal trajectories to the curves where u2 is equal to a constant. This can be seen in a similar manner as in the case of geodesic parallel coordinates. The curves where u1 is equal to a constant are called geodesic circles. The corresponding value of u1 is called the radius of such a circle. In consequence of this first fundamental form for geodesic coordinates, we have that g sub 1 1 equals 1 and g sub 1 2 equals 0. For later purposes, it is necessary to investigate the behavior of g sub 2 2 at capital P. We have that dv1 equals cosine of u2 times du1 minus u1 times sine u2 times du2, and that dv2 equals sine of u2 times du1 plus u1 times cosine of u2 then times du2. If we insert these expressions into the first fundamental form, g sub alpha beta star times dv alpha times dv beta, we find that du2 squared has the coefficient g sub 2 2 equals u1 squared then times the quantity g star sub 1 1 times the sine squared of u2 minus 2 times g star sub 1 2 times the sine of u2 then times the cosine of u2 plus g star sub 2 2 times cosine squared of u2. Since the partial derivatives of g star sub alpha beta vanish at capital P, for which you can refer to above, we obtain from this that the limit as u1 approaches 0 of g sub 2 2 equals 0, and the limit as u1 approaches 0 of partial square root of g sub 2 2 partial u1 equals 1. From the previous relation for Gaussian curvature for the case of geodesic coordinates, we have that partial squared of the square root of g sub 2 2 partial u1 squared is equal to negative capital K times the square root of g sub 2 2. So we thus have that partial cubed of the square root of g sub 2 2 partial u1 cubed is equal to negative capital K times partial square root of g sub 2 2 partial u1 then minus partial capital K partial u1 times the square root of g sub 2 2. And therefore the limit as u1 approaches 0 of partial cubed of the square root of g sub 2 2 partial u1 cubed is equal to the negative limit as u1 approaches 0 of capital K, which is equivalent to negative capital K naught. Since the square root of the quantity g sub 2 2 in terms of u1 and u2 is equal to the square root of g sub 2 2 in terms of 0 and u2, then plus u1 times partial square root g sub 2 2 partial u1 evaluated at u1 equal to 0, plus u1 squared over 2 then times partial square root of g sub 2 2 partial u1 squared evaluated at u1 equals 0, plus etc. We thus obtain that the square root of g sub 2 2 equals u1 minus capital K naught times u1 cubed over 6 plus etc. Or g sub 2 2 equals u1 squared minus capital K naught times u1 to the 4th over 3 plus etc. Where etc. or ellipses as written denotes or indicates functions of u1 and u2 which vanish at capital P of higher than 3rd or 4th order respectively. Because of the previously stated relation for Gaussian curvature for the case of geodesic coordinates, the length of capital S of a geodesic circle is thus given by the expression capital S equals the integral from 0 to 2 pi of the square root of g sub 2 2 then du2 equals 2 pi times u1 naught minus pi times capital K naught over 3 times u1 naught cubed plus etc. From this, the formula of Puiseux and Bertrand from 1848 for the Gaussian curvature capital K naught at the center capital P of the geodesic polar coordinate system, capital K naught equal to the limit as u1 naught approaches 0 of the fraction with the numerator 3 times the quantity 2 times u1 naught times pi minus capital S closed quantity over a denominator of u1 naught cubed times pi follows. In consequence of the first fundamental form in the case of geodesic coordinates and the previously given relation for g sub 2 2, the Christoffel symbols with respect to geodesic polar coordinates vanish at the center capital P, for which refer back to the explicit formulae for the Christoffel symbols in section 47. Problem 53.1. Find a representation given by a vector x in terms of coordinates u1 and u2 of the sphere where u1 and u2 are geodesic polar coordinates. Since the geodesics of a sphere are its great circles, the coordinates u1 and u2 occurring in the representation of a sphere from previously are geodesic coordinates. If we write that the vector x in terms of u1 star and u2 star is equal entry-wise to r cosine u1 star times cosine u2 star, and then r cosine u1 star sine u2 star, and then r sine u1 star, we have that ds squared is equal to r squared times the quantity du1 star squared plus cosine squared root of u1 star, then times du2 star squared closed quantity. Setting u1 equal to r times u1 star and u2 equal to u2 star, the first fundamental form is of the type given in section 52. The curves u2 equal to a constant form a geodesic field except at the poles. In the representation given by the vector x in terms of u1 and u2, which is equal entry-wise to r cosine u2 times sine of u1 over r, and then r times sine u2, then times sine of u1 over r, and then r times cosine of u1 over r. In this representation, u1 and u2 are geodesic polar coordinates with the center at the quote-unquote north pole, capital P, of the sphere, and u1 is the arc length of the geodesics, u2 equal to a constant measured from this north pole at capital P. Section 54, Theorem of Gauss-Bonnet, Integral Curvature. The Gauss-Bonnet theorem is one of the most important theorems of the theory of surfaces. It was first published by Pierre-Ossien Bonnet, who lived from 1819 to 1892, published in 1848, for which refer to his work Mémoires sur la théorie générale des surfaces. But it was probably already known to Gauss. This theorem is an example of differential geometry in the large, which was explained in the preliminaries section 2. Moreover, it is analogous to Green's theorem and can be obtained from this theorem, for which refer to Jean-Gaston Darboux's work Leçons sur la théorie générale des surfaces, volume 3. The double integral over capital S of capital K d capital A occurring in the Gauss-Bonnet theorem is called the integral curvature of the portion capital S of a surface under consideration. Theorem 54.1, the Theorem of Gauss-Bonnet. Let capital S be a simply connected portion of a surface for which a representation given by the vector x in terms of u1 and u2 of class r greater than or equal to 3 exists, and whose boundary capital C is a simple closed curve which has a representation x in terms of the function u1 of s and the function u2 of s of class r star, which is greater than or equal to 2, where s is the arc length of capital C. Let kappa sub g be the geodesic curvature of capital C, and let capital K be the Gaussian curvature of capital S. Then the integral on capital C of kappa sub g ds plus the double integral on capital S of capital K d capital A is equal to 2 pi, where d capital A is the element of area of capital S. The integration along capital C has to be carried out in such a sense that capital S stays on the left side. The proof is as follows. We introduce on capital S allowable orthogonal coordinates u1 and u2 in the following way. Let capital P be an arbitrary point of capital S, and let capital C naught be a sufficiently small geodesic circle with center at capital P. Then we assume u1 and u2 are geodesic polar coordinates in the interior of capital C naught, for which refer back to section 53. The curve capital C is given by u1 equals 1, and on capital C the coordinate u2 is equal to the arc length lowercase s. The existence of such a coordinate system may be proved as follows. In forthcoming section 62, we shall see that under the above assumptions, capital S can be mapped conformally into a plane capital E. Let capital S star, capital C star, and capital C star naught be the images of capital S, capital C, and capital C naught, respectively, in capital E. As is known from the theory of complex analytic functions, the portion of capital S star bounded by capital C star and capital C star naught can be mapped conformally onto a plane ring bounded by two concentric circles. The circles concentric to these bounding circles correspond to a family of closed curves in S star, which cover capital S star schlicht, which I think is German for simple. The inverse images of these curves and their orthogonal trajectories on capital S, together with the geodesic circles in the interior of capital C naught and their orthogonal geodesics through capital P, form the coordinate curves of the coordinates u1 and u2. According to the previously given formula for geodesic curvature, when the coordinates u1 and u2 are orthogonal, but specifically when u1 is a constant, the geodesic curvature kappa sub g of capital C is then given by the expression kappa sub g of capital C is equal to 1 over the square root of g sub 11 times g sub 22, then times partial square root of g sub 22 partial u1. Since u2 equals lowercase s on capital C, we have g sub 22 equals 1 on capital C. We thus obtain from the previously given expression for kappa sub g that the integral on capital C of kappa sub g ds equals the integral on capital C of 1 over the square root of g sub 11 times partial square root root g sub 2 to partial u1, then du2. Let capital S naught be the domain bounded by capital C naught. From the equation of Gauss, we find that the double integral on capital S minus capital S naught of capital K d capital A is equal to the double integral on capital S minus capital S naught of capital K times the square root of g du1 du2, which is equal to the negative double integral on capital S minus capital S naught of partial with respect to u1 of the quantity 1 over square root of g sub 1 1, then times partial square root g sub 2 2 partial u1 du1 du2, minus the double integral on capital S minus capital S naught of partial with respect to u2 of 1 over the square root of g sub 2 2, then times partial square root g sub 1 1 partial u2 du1 du2, which is equivalent to the Jacobian capital J sub 1 plus the Jacobian capital J sub 2. The integration with respect to u2 has to be carried out along closed curves, hence the Jacobian capital J2 equals 0, and we therefore have that the double integral on capital S minus capital S naught of capital K d capital A is equal to the Jacobian capital J1, which is equal to the negative integral on capital C of 1 over the square root of g sub 1 1, then times partial square root g sub 2 2 partial u1 du2 plus the integral on capital C naught of 1 over the square root of g sub 1 1, then times partial square root g sub 2 2 partial u1 du2. Hence, in consequence of the previously given relation for the integral on capital C of the geodesic curvature with respect to arc length, we have that the integral on capital C of kappa sub g ds plus the double integral on capital S of capital K d capital A is equal to the limit as capital C naught approaches capital P of the integral on capital C naught of 1 over the square root of g sub 1 1 times partial square root g sub 2 2 partial u1 du2. Since the integrals on the left hand side of what was just derived exist, the limit on the right hand side also exists. In capital C naught, according to the relation for the first fundamental form for geodesic coordinates, g sub 1 1 equals 1, and according to the limit as u1 approaches 0 of partial square root g sub 2 2 partial u1 equals 1, and what was just derived therefore becomes identical with the statement of the Gauss-Bonnet theorem. The Gauss-Bonnet theorem can also be formulated for a simply connected portion of a surface which is bounded by finitely many arcs, so that at the endpoints, the tangents to those arcs have different directions, that is, the boundary capital C may have cusps. In a neighborhood of any cusp, capital E, we replace capital C by an arc capital C sub G of a geodesic circle of radius r, for which refer back to the previous section, section 53, whose tangents at the endpoints, capital A and capital B, coincide with that of capital C, for which refer to figure 61. We then let r approach 0. We have the limit as r approaches 0 of the integral on capital C sub G of kappa sub G d sigma is equal to the limit as r approaches 0 of the integral on capital C sub r of 1 over r times r d phi equals alpha, where d sigma is the linear element of capital C sub G and capital C sub r is an arc of a circle of radius r. The angle alpha, which is greater than or equal to negative pi and less than or equal to pi, is the directed angle of rotation of the tangent to capital C at capital E. Now, if capital C has the cusps E1, E2, etc. through En, with corresponding interior angles beta sub nu equals pi minus alpha nu, where nu is equal to 1, 2, etc. through n, for which refer to figure 62 for a depiction, then the statement of the theorem of Gauss-Bonnet as previously can be reformulated instead as the integral on capital C of kappa sub g ds plus the sum on the index nu from 1 to n of alpha sub nu plus the double integral on capital S of capital K d capital A is equal to 2 pi. Or, replacing alpha sub nu by pi minus beta sub nu, the quantity n minus 2 times pi plus the integral on capital C of kappa sub g ds plus the double integral on capital S of capital K d capital A is equal to the sum on the index nu from 1 to n of beta sub nu. A portion of a surface bounded by a simple connected broken line capital C of geodesic arcs is called a geodesic polygon. In this case, we obtain from the modified statement for the theorem of Gauss-Bonnet that we just had in terms of a sum for beta sub nu. We have that the sum on nu from 1 to n of beta sub nu equals the quantity n minus 2 closed quantity times pi plus the double integral on capital S of capital K D capital A, where n is the number of cusps in capital C. If in particular the non-zero Gaussian curvature capital K is constant, the area of the geodesic polygon capital S becomes capital A of capital S equals 1 over capital K times the quantity sum on nu from 1 to n of beta sub nu minus the quantity n minus 2 closed quantity times pi closed outer quantity. If Gaussian curvature capital K is 0, we obtain from the relation for the sum on nu from 1 to n of beta sub nu derived previously the well-known formula for the sum of the angles of an n-sided polygon in a plane. In the case n equals 3, we find from this same relation for the sum of beta sub nu, if at every point of a geodesic triangle the Gaussian curvature is positive, the sum of the angles of that triangle is greater than pi. For example, geodesic triangles on a sphere. If at every point of a geodesic triangle the Gaussian curvature capital K is negative or less than 0, that is, the sum of the angles is less than pi. For example, geodesic triangles on a pseudosphere, for which refer to the forthcoming section 93. The deviation of the sum of the angles of a geodesic triangle from the value pi is called its excess. According to this sum, once again, of beta sub nu, the excess is equal to the integral curvature of the triangle. If we set n equal to 0, we obtain from this sum of beta sub nu Theorem 54.2. On a surface capital S of r greater than or equal to 3, for which the Gaussian curvature capital K is less than or equal to 0 everywhere, there do not exist closed geodesics such that just one of them constitutes the entire boundary of a bounded portion of capital S. For example, a plane gives the simplest illustration of this theorem. Another example is the cylinder of revolution. That is, the parallels are closed geodesics, namely circles on the cylinder, but a single one of those geodesics is not the entire boundary of a bounded portion of the cylinder. Since multiply connected pieces of surfaces can be cut so that they become simply connected, for which refer to figure 63 below, we may easily formulate the Gauss-Bonnet theorem for such pieces. The path of integration for the integral of kappa sub g ds has to be chosen as shown by the arrows in the figure. Every section, S1, S2, etc. is passed twice, once in each of the two directions. Hence, the integrals along those sections do not contribute to the above integral, but at the endpoints of each of those sections, the tangent makes 4 rotations through an angle pi over 2. From each section, we thus have the contribution 2 pi. Problem 54.1. Apply the Gauss-Bonnet theorem to a plane circular ring. Let the circular ring be bounded by the circles capital C1 and capital C2, whose respective radii are R1 and R2. We cut the ring along a segment with endpoints on those circles. Since the ring is a plane, the Gaussian curvature capital K is equal to 0. Hence, the integral on capital C1 of kappa sub g ds plus the integral on capital C2 of kappa sub g ds plus 2 pi equals 2 pi. For plane curves, the magnitude of kappa sub g equals kappa, curvature, and therefore, in our case, the integral on capital C1 of kappa sub g ds plus the integral on capital C2 of kappa sub g ds is equal to the integral from alpha equals 0 to 2 pi of 1 over r1 then times r1 dA minus the integral from alpha equals 0 to 2 pi of 1 over r2 then times r2 dA, which is equal to 0. This is in agreement with the preceding relation. Section 55. Applications of the Gauss-Bonnet theorem to closed surfaces. An important result of topology of surfaces is the theorem that any closed orientable surface, for which refer back to the previous section 34, is homeomorphic, for which a definition can be found in the previous section 3 in the preliminaries chapter, to one of the infinity 1 normal types of closed orientable surfaces. These types can be obtained from a sphere by attaching 0, 1, etc. through p, etc. handles, respectively, see figure 66. The number lowercase p is called the genus of the surface. Any closed surface of genus 0 or 1 is homeomorphic to a sphere or a torus, for which refer to section 43, which was on a torus, respectively. It is most remarkable that the integral curvature of a closed orientable surface of class r greater than or equal to 3 is completely independent of its particular shape but depends on its genus only. We have Theorem 55.1. Any closed orientable surface capital S of genus lowercase p for which a representation of class r greater than or equal to 3 exists has the integral curvature given by the double integral integral on capital S of capital K d capital A, which is equal to 4 pi times the quantity 1 minus lowercase p closed quantity. In particular, the integral curvature of the torus vanishes. The proof is as follows. In case A, consider p equals 0. We cut capital S into two pieces, S1 and S2, in such a manner that the section capital C is a curve of the type indicated in Theorem 54.1. Then we have that the integral on capital C of kappa sub g ds plus the double integral on capital S sub I of capital K d capital A is equal to 2 pi, and I can be equal to 1 or 2. Obviously, the sense of integration along capital C in the case of S1 is opposite to that in the case of S2. By adding the two equations for each of the cases of I for the previous relation, we thus obtain that the double integral on capital S of capital K d capital A is equal to 4 pi. Now consider case B where p is greater than or equal to 1. No, hey, oh my gosh. Are you kidding me right now? I'm going to smack a cat's ass. Don't try me, little boy. You better not try me. That's right, you're gonna have to pout like a little sad little boy because you messed up. You messed up. Consider now case B where p is greater than or equal to 1. We choose any point capital P on the surface and cut the surface by means of 2 times lowercase p cuts starting from capital P and returning to capital P in such a manner that we obtain a simply connected surface, and that at capital P, the angle between neighboring cuts is equal to 2 pi over 4 times lowercase p. Since each cut serves twice as path of integration, once in each direction, the integrals of kappa sub g ds along the cuts do not contribute, but we have contributions from each of the 4 times lowercase p rotations of the tangent, which takes place if at capital P we proceed from one cut to the next. On each of these occasions, the tangent is rotated through an angle given by pi minus 2 pi over 4 times lowercase p, which is equal to pi times the quantity 1 minus 1 over 2 times lowercase p closed quantity. Therefore, according to the Gauss-Bonnet theorem, 4 times lowercase p times pi times the quantity 1 minus 1 over 2 times lowercase p closed quantity plus the double integral on capital S of capital K d capital A is equal to 2 pi, and this completes the proof. Problem 55.1. Determine the integral curvature of a sphere and of a torus by direct computation. A sphere capital S of radius lowercase r has the area capital A equals 4 pi r squared and the constant Gaussian curvature capital K equal to 1 over r squared. Therefore, the double integral on capital S of capital K d capital A is equal to 1 over r squared times the double integral on capital S of d capital A, which is equal to capital A over r squared, which is equal to 4 pi. In the case of the torus, we have from the representation of the torus in the previous section 43 on a torus, d capital A is equal to r times the quantity r naught plus r times cosine u2 closed quantity du1 du2, and capital K equals cosine of u2 all over r times the quantity r naught plus r times cosine u2 closed quantity. Again, refer back to section 43 on a torus. And therefore, the double integral on capital S of capital K d capital A is equal to an integral from 0 to 2 pi of another integral from 0 to 2 pi of cosine u2 du1 du2, which is all equal to 0. That is the end of section 55. That is the end of chapter 5. And that is the end of this video. I will see you guys in the next one. Peace. U tau double dot plus Christoffel sub okay, here we go. U tau double dot plus Christoffel sub nu sigma okay, here we go.
Sure enough, I've been able then to develop a structure which has where none of the compression members touch one another. If you have a basketball and you put air in it and you put a little more air, it gets harder and harder. The air doesn't, the molecules of gas don't go to the center and explode outwardly. That would be vibrating. They go, now, each one of these sticks you're looking at here is part of that pattern. So this is then the model of the molecules of gas are doing inside the basketball. And this thing just bounces like the basketball. Now,